Here are some important ideas about vectors in two dimensions, because we're now thinking about two-dimensional motions. So displacement vectors and velocity vectors and acceleration vectors and force vectors will all be in two dimensions. We know that for any vector, it has two pieces of information, a magnitude and a direction. And in two dimensions, that means you need two numbers to specify that magnitude and direction. Imagine this, here's an XY coordinate system, and imagine this displacement vector representing some motion that started here and ended here. So as always, the displacement vector points straight from the initial location directly to the final location, and the magnitude of the displacement vector is the distance between the starting point and the finishing point. And the two numbers that would completely specify that displacement vector are the magnitude of the displacement vector and another number that represents an angle, and that angle will tell you the direction of the in which the vector points. The angle, important to note here, the angle is always an angle with respect to some coordinate axis, and you always have to be sure to name that coordinate axis. For instance, in this case, if theta is, let's say, 30 degrees, that means the direction of displacement d is 30 degrees clockwise with respect to this axis, the negative x-axis. That is, if you're looking along the negative x-axis, then rotate clockwise 30 degrees, and you'll be pointing in the direction of displacement vector d. So two numbers are needed to completely specify a vector in two dimensions. Magnitude and a direction angle are two of those numbers, or an alternate pair of numbers that works equally well are the two so-called components of a vector. When we talk about components, what we're really doing is reimagining that vector as something going on along one coordinate axis, and then something going on along the other coordinate axis. For instance, this displacement vector d, which is motion that takes you from here to here, you can think of that displacement as first this displacement along the x-axis, then this displacement along the y-axis. And this displacement along the x-axis we call the x-component of displacement d, and this displacement along the y-axis we call the y-component of displacement d. And the movement, the displacement along the x direction, plus that movement, displacement along the y direction, is equal to the displacement d that took you from here to here. This path and this path are equivalent paths. Equivalent in the sense that they get you from the same starting point to the same finishing point. And that's how we think about components. And when we start thinking about forces, the components of those forces become quite important. That if you have a force that points along neither the x-coordinate axis, nor is it parallel to the y-coordinate axis, but it's at some diagonal angle, it becomes much easier to reimagine that force as a certain amount of force along the x-axis plus a certain amount of force along the y-axis. Now notice that the actual displacement and its two components form a right triangle, and that's important. You should always get into the habit of imagining a vector and its components as forming a right triangle. And it turns out the relationship between a vector and its components is just like the relationship between the hypotenuse of a right triangle and the two perpendicular sides. For example, if we have these two numbers that completely specify the variable, but the two components would just as easily specify the vector. So there ought to be some way of converting from one pair to the other pair. That is, if you know what the magnitude and direction angle are, you ought to be able to figure out what the components are. If you know what the components are, you ought to be able to figure out what the magnitude and direction angle are. And you can do that if you recognize the fact that a vector is related to its components the same way that the hypotenuse of a right triangle is related to the two perpendicular sides. And that's where a little bit of trigonometry comes in. It's only a little bit of trigonometry, but you have to be very, very comfortable and familiar with that little bit of trigonometry. The three fundamental trigonometric functions, sine, cosine, and tangent, can all be defined as ratios of lengths of sides in a right triangle. For example, if you look at this right triangle and consider this angle here, here's the hypotenuse, h, and then here's the side that's opposite to the angle that we're paying attention to, and then here's the side that's adjacent, ADJ for adjacent, adjacent to the angle that we're looking at. And we can define sine of this angle as equal to the ratio of the opposite side to the hypotenuse. Opposite side to the hypotenuse. And we can define cosine of this angle as the ratio of length of the adjacent side to length of the hypotenuse, adjacent over hypotenuse. And the third trigonometric function, tangent, tangent of angle theta, we can define as the ratio of the length of the side opposite to length of the side adjacent. Right? Tangent of the angle equals opposite over adjacent. Now, rewrite these two things a little, just a little bit. Rewrite the rule involving sine as length of the opposite side equals hypotenuse times sine of the angle that's opposite to this side. So h, length of hypotenuse times sine of this angle would give the length of this side. And similarly, rewrite cosine as adjacent side equals hypotenuse times cosine of the angle. That is, hypotenuse times cosine of this angle gives you the length of the side that's adjacent to that angle. And that's basically how we can convert information about a magnitude and a direction angle into information about components of vectors. For example, here's our xy coordinate system. And imagine that vector, displacement vector like that. We'll say that the magnitude of that displacement vector is 10 meters. And we'll say that the direction angle we're taking this for our direction angle, is 30 degrees. That is, D points 30 degrees counterclockwise with respect to the negative y-axis. And you have to say all that other stuff in order to completely specify the direction. You can't just say 30 degrees, you have to say 30 degrees with respect to what axis and which way with respect to that axis, clockwise or counterclockwise. But now we've got magnitude and direction angle. We can use these rules to figure out the two components. The side opposite, just imagine the triangle that's formed by the vector itself as the hypotenuse, and then the two components as the perpendicular sides of the right triangle. The side that's opposite to the 30-degree angle is the y component of that displacement. And dy is pointing, y component of that displacement is pointing in the positive y direction, so we can represent it as a positive number. And so its value is just going to be the same as the length of this opposite side, which is just hypotenuse times sine of the angle, 30 degrees. So hypotenuse of 10 meters, sine of 30 degrees, and that comes out to 5 meters. Sine of 30 turns out to be exactly 1/2. And then the adjacent side of this triangle corresponds to the x component, dx. Dx points in the negative x direction, so the actual value of dx is -1 times the length of this side of the triangle. In other words, -1 times the side that's the length of the side that's adjacent to the 30-degree angle. So it's minus hypotenuse of 10 times cosine 30 degrees, and that comes out to minus 8.7 meters. So there it is. By using just a little bit of trigonometry, we can jump from identifying that, specifying that vector with a magnitude and direction angle to specifying it with the two components. One more example. Here's our xy coordinate system, and our vector will be something like this. Just imagine another displacement vector. So there was some kind of motion that started here and ended here, and that's the displacement vector that represents that motion. Displacement vector, I'll call it d again, and its magnitude, we'll say this time 6 meters. The distance between the starting point and the finishing point is 6 meters. And for our direction angle, we'll take an angle with respect to the positive y-axis. So there's our angle right there, and we'll say that angle is 20 degrees. So we've got magnitude and direction, and from that we can figure out the components of that vector. The vector itself is like that, so its x component and its y component would look like that. it's always the case that adding the two vector components gives you the vector itself. And in this case, let me redraw that a little bit. Here's the vector d. Here's the y component. There's the x component. And there's the 20-degree angle that we're using. So let's figure out the x component first. It points in the positive direction, so the numerical value of that x component is just equal to the length of this side, which is now, in this case, the side opposite to the angle that we're using. Since it's the side opposite, we have to use sine, not cosine. We're using this rule. So dx is length of the hypotenuse times sine. Hypotenuse was 6 meters times sine 20 degrees. And then if you ask your calculator what the sine of 20 degrees is and then multiply that by 6, you'll come up with about 2.1 meters for this length here. And then dy is this side here, and dy is pointing in the positive y direction, so the numerical value of dy will be the same as the length of this side, which is the side that's adjacent to the angle. And whenever we're talking about an adjacent side, the trigonometric function we use is cosine. And so hypotenuse times cosine, 6 meters times cosine 20 degrees, and then ask your calculator to do that calculation, and you'll come up with 5.6 meters. In other words, the displacement that takes you from here to a point 6 meters away, when you move along an angle that was 20 degrees clockwise with respect to the positive y-axis. That's the same as going 5.6 meters straight in the positive y direction and then 2.1 meters straight in the positive x direction. All right, now those are examples of how, if you know the magnitude and direction angle, you can find the components. How about the other way around? If you know the components, how can you find the magnitude and direction angle? So imagine our vector, and there are its components. Because the relationship between a vector and its components is the same as the relationship between the hypotenuse and the two perpendicular sides of a right triangle, we can use everything we know about right triangles. And one thing we know about right triangles is the Pythagorean theorem. The square of the length of the hypotenuse equals sum of the squares of the other two sides. The length of the hypotenuse here corresponds to the magnitude of d. So, magnitude of d squared, which corresponds to the length of the hypotenuse squared, equals sum of the squares of the other two lengths. Magnitude of dx corresponds to the length of this side, square it. magnitude of dy corresponds to the length of this side squared. So sum of the squares of the two perpendicular sides equals the square of the hypotenuse, or magnitude squared of the vector itself equals this this combination here involving the components. Or to put it another way, magnitude of the vector is just the square root of this sum. All right, that's how we get the magnitude of the vector if we know the components. How do we get a direction angle for the vector if we know the components? For this we use the other trigonometric function, tangent. Remember, tangent of an angle is a ratio of the length of the side opposite to length of the side adjacent. So if we take that as our direction angle, that is, right, in this case, the vector d points theta degrees counterclockwise with respect to the positive x-axis. Rotate theta degrees counterclockwise starting from the positive x-axis, and you're then pointing in the direction of d. And tangent of that angle is a ratio of that length to that length. And this length just corresponds to the magnitude of dy. And the length of the side adjacent just corresponds to the magnitude of dx. So what you're looking for in this equation, right, you know these numbers, you're trying to solve for theta. What you're really looking for then, in other words, is the angle that has this number for its tangent. And to find that number, you need to use the inverse tangent function. That is, tangent to the -1 power is how we write the so-called inverse tangent. The inverse tangent of that ratio, magnitude of dy over magnitude of dx, is the angle. Now it's much, remember, this is the side that's opposite to the angle. This is the side that's adjacent to the angle. And as we saw in the previous example, sometimes it might be the x component that's opposite and the y component that's adjacent. So this is how things work for this particular triangle and this particular angle. Would be a little bit different if we chose a different angle. But what we can say is true always is that tangent of the angle is just a ratio of the length of the side opposite, the magnitude of the component opposite to theta, divided by the length of the side adjacent, that is the magnitude of the component adjacent to the angle. Now, it's not a lot of words there. Let's see how it actually works out in practice. So here's our coordinate system. And let's say our vector is made up of our displacement vector is made up of two components. An x component in the negative x direction, and that x component is -2 meters. And then a y component in the negative y direction, and that y component is -5 meters. So the actual displacement is the sum of this much motion in the x direction plus this much displacement in the y direction. In other words, you've got a starting point here and an ending point here, and you could have gotten from the start to the finish by either this path or a direct path. Two different paths that take you from the same starting point to the same ending point, so they are equivalent displacements. The magnitude of that displacement we just figure out with the Pythagorean theorem, because it's the hypotenuse of a right triangle, and dx and dy are the magnitudes of dx and dy are the two perpendicular sides. So just use that rule. Square root of the magnitude of dx squared, so -2 squared, gives us 4 square meters. And then magnitude of dy squared, which is -5 meters squared, so that gives us 25 meters squared, or the square root of 29 square meters. Which comes out to about 5.6 meters. Or excuse me, 5.4 meters. That's the magnitude of the vector. Now for the direction angle. That's where we use tangent of an angle. And if we say that this is our direction angle, then tangent of the direction angle is just the length of the opposite side, which is the magnitude of dy, 5 meters, divided by length of the adjacent side, which is just the magnitude of the x component, 2 meters. So tangent of theta is equal to 5 halves. Theta is the number that has 5 halves for its tangent. So theta is inverse tangent of 5 halves, and that comes out to 68 degrees. But 68 degrees with respect to what? 68 degrees counterclockwise with respect to the negative x-axis. Counterclockwise with respect to the minus x-axis. If you point in the negative x direction and rotate counterclockwise by 68 degrees, then you'll be pointing in the direction of D. Okay, and then one last example. Here's our coordinate system. And we'll say that this time our displacement is a displacement in the positive x direction of 6 meters, and then a displacement in the negative y direction. That displacement is in the negative y direction, and it's 5 meters. And then if you start here and then take this path, and this is your ending point, that's the same displacement as if you took that path So that displacement d is just the same as displacement dx plus displacement dy. The vector itself is the same as the sum of its components. So magnitude, we use Pythagorean theorem. Magnitude of that displacement is just square root of the sum of the squares, of the lengths of the other two sides, and the lengths of the other two sides correspond to the magnitudes of those component vectors. So it's, go back to the rule there, square root of dx squared. Dx squared is 36 square meters, plus dy squared, and dy squared is 25 square meters. So that's the square root of 61 square meters, which comes out to about 7.8 meters. If you move 6 meters along the positive x-axis and then 5 meters in the negative y direction, you're now at a point that's 7.8 meters away from where you started. And now for the direction angle, let's say that this is our direction angle, and so the tangent of that angle is just the length of the opposite side. That would be the magnitude of dy, 5, divided by the length of the adjacent side, which would be the magnitude of dx, 6. So this angle is the angle that has 5/6 for its tangent. So theta is the inverse tangent of 5/6, and that comes out to about 40 degrees. 40 degrees with respect to what? This direction is 40 degrees away from the positive x direction. So that direction angle is 40 degrees clockwise with respect to the positive x direction. If you point in the positive x direction and rotate clockwise by 40 degrees, you're pointing in the direction of d. 40 degrees clockwise with respect to the positive x direction. And just one more thing here. Let's say we're looking at our displacement vector d here. D had that magnitude of 7.8 meters, and that involved some motion in the y direction of 5 meters in the negative y direction, and then 6 meters of motion in the positive x direction. Could just as easily have chosen that for a direction angle. Let's see how that works out. Either of the two non-90 degree angles in the right triangle would work perfectly well for specifying the direction angle. So finding this angle, you use tangent again, and tangent of that is the ratio of opposite over adjacent, but now opposite is the magnitude of the x component. tangent of that angle is length of the opposite side, which is magnitude of dx, which is 6 meters, divided by length of the adjacent side, which is in this case dy. So length of this side corresponds to magnitude of dy, which is 5 meters. So this direction angle is a number that has 6/5 for its tangent. So the angle is the inverse tangent of 6/5, which comes out to 50 degrees. Not surprising because this angle here was 40 degrees. But 50 degrees with respect to what? Here's D, here's the angle. So 50 degrees counterclockwise with respect to minus y. That is, start by pointing in the minus y direction, rotate counterclockwise by 50 degrees, and then you're pointing in the direction of the displacement vector d. The direction angle is 50 degrees counterclockwise with respect to minus y. Can't forget that minus. Okay, everything else that's all the trigonometry you need to know, but you need to know it well. You'll have plenty of chances to practice and get to the point where you know it well. But this is the idea. When we start thinking about in more detail about situations involving forces and the accelerations they cause, we will be often breaking down the motion into its components. What is the net force along the x direction? In other words, what's the x component of the net force? What is the net force along the y direction? In other words, what is the y component of the net force? We'll be using components of x and y components of net force very often. And as we'll see, to figure that out, we'll need to be able to figure out the x and y components of the individual forces. But that'll come next time.